March 2022, paper 6, variant 2. In question 1, student investigates the extension of a spring and uses it to determine the weight of a meter ruler. So you have spring is shown in full size, the length, and then the length, the extended length. On figure 1.1, measure the L0. Can I measure L0 without any load? Yes, I can measure L0 without any load. The extension would be around 2 centimeters. Again, if your reading is slightly less than 2 centimeters, it is okay. So if your reading is 1.9, 1.8, it would be okay due to the printing error. On figure 1.2, measure the stretched length LS. LS should be 6.2 centimeters. If your reading is 6 centimeters, it would be acceptable. From these two readings, we can find extension. Maybe later on he would ask about the extension. Student attaches a meter ruler to the spring with a wire hook. She ensures that the meter ruler is horizontal. Briefly describe how to check if the meter ruler is horizontal. Again, how can I make sure it's horizontal? By measuring the distance from either side. You have to measure this distance and this other distance. Make sure that they are equal, right? You may draw a diagram. We don't need to draw the diagram. So she measures the distance from the ruler from to the bench on either side of the ruler, okay, and make sure that they are equal. They are equal, okay. Student moves the load W. Distance is 20, 30, and 40, 50 centimeters. She reads the length using the values, plot a graph of L on the y-axis, L on the y-axis, D on the x-axis, and start from 0. D on the x-axis. So, okay, no problem. The L on the y-axis, you start from 0 all the way up to 9. So I guess 2, 4, 6, 8, 10 would be suitable for the length. And as for the distance, maybe 10, 20, 30, 10, 20, 30, 40, 50, and 60. Yes, this is definitely suitable. 20 and 6.2. 20 and 6.2. So 6.2. Let me zoom in. Okay, so 10, 20, 6.2. This is 6.2. And then 30 and 7.1. 30 and 7.1. This is 7.1. 47.6. 7.6. 3 squares above 7. 50 and 8.3. Square and a half above 8.3. And then 60 and 9. 60 and 9. Okay, not too bad. These points are quite good. From your graph, determine length when the value, okay, when the value of D is 0 centimeters. So basically, we need to draw the graph, we need to draw the line of best fit, and okay, need to draw the line of best fit and extend the line until it reaches, okay, extend the line until it reaches the y-axis, until it reaches the y-axis this way, right? So the length, okay, would be around 5. Length would be around 5. This is 5. 5.0 centimeters. Let me remove this line. Calculate WR. the weight using your value from L. Okay, using your, this is value L. This is capital L, 5.0. WR would be 2L, which is 5, minus L note. What was L note? Huh? It was 2.0. Then LS is 6.2. 2.0 and 6.2. Okay, 5 minus 2.0. And then LS, which was 6.2, minus 2, times K, which is 1, times 1. Just to make this whole whole equation in newtons. 2 times 3 over 4.2, which is 1.4, okay, 1.4 newtons. If your value is 1.4, if your value is 1.5, it's okay. It depends on the value of the length. If your value of the length here was, for example, 5.2, again, it would be okay. There is a range. There is an acceptable range. So my value for the WR is 1.4 newtons. It's okay, within the limits. I guess the range would vary between 1.3 and 1.6. It is sometimes difficult to position the load on the scale correctly at a distance d from the pivot. Suggest one change to the apparatus to overcome this difficulty. So as you place the load on the meter ruler, it is sometimes quite difficult. How can I overcome this difficulty? Okay, how can I overcome this difficulty? Yes, you can somehow attach the load to a string, for example. Okay, you can attach the load to a string. You actually can come up with several ideas. You can come up with several solutions. This load, okay, if you check out the if you check out the figure again, you want to place this load at this point, right? It's sometimes difficult to place it exactly on this point. If I want to change the position, if I want to place the load at this point or at this point or whatever point on the ruler, it might be a bit difficult. So how can I do that? By attaching this load to a string, for example, and fixing this string somehow above, okay, somehow above the ruler. If you fix the string above the ruler, it would be rather a lot more accurate. Okay, it would be a lot more accurate. That's it. Or you can actually hold the string. You can hold it. You don't have to attach it to something. You can just hold the string or hold this load above the point. Okay, so attach to a string, attach the load to a string, and hold it above the point, or hold it above the mark or whatever. So just one possible source of inaccuracy other than the difficulty described, other than this difficulty in DI. Assume that the experiment is carried out carefully. So you have several inaccuracies. Okay, you have several inaccuracies. For example, you might have a zero error, right? You might have a zero error in the spring, which is which has where was the spring? So I have this spring. There might be a zero, or this spring isn't actually proportional. For example, this spring has some sort of error, or this spring isn't uniform. If the diameter of the loops in the spring aren't uniform, then the readings wouldn't be directly proportional, right? What else? For example, hmm, this load, you have this load, for example, he said that it's 1 Newton. What if this load was not 1 Newton? What if this load was actually 1.1 or 1.2 newtons? Then this whole experiment would be wrong, right? So these are all possible sources. Again, possible sources. Are there other possible sources? Yes, there are possible sources, other possible sources. If you come up with a new possible source, which is, well, rather okay, rather acceptable, yes, then it would be accepted as a solution, as an answer. Okay, so for example, the 1 Newton load wasn't actually 1 Newton. Okay, the 1 Newton load was not accurate. It could be actually greater or less than 1 Newton. Hmm. Question 2. Can I find theta r? Yes, I can find theta r, which is 23 degrees Celsius. Student uses the apparatus shown in figure 2.1, and 2.2, and 2.3. So in 2.2, you have beaker A and the lid. 2.3, you have beaker A with the lid inside beaker B. There is a gap, an air gap between these two beakers. Okay? The student removes the lid from beaker A. He pours 150 centimeters cubed of hot water, replaces the lid, inserts the thermometer, and takes the temperature every 30 seconds. Describe two precautions that can be taken. Two very important precautions would be to take the reading perpendicularly. Take the reading perpendicularly from the thermometer. Take, okay, reading perpendicularly. To avoid, to avoid parallax error. And then another precaution would be to leave the thermometer, leave the thermometer until the readings, okay, until the reading stops increasing. Soon pours away the water from beaker A. He then places beaker A inside beaker B so that there is an air gap between the two beakers, and he repeats the experiment. Can I add units? Can I complete the table column headings? Yes, the time is in seconds. Temperature in theta in degrees Celsius and degrees Celsius. Write a conclusion whether the air gap affects the rate of cooling or not. Okay, beaker A without the air gap, it was 85, and then it's 67.5. What's 85 minus 67.5? This is a difference of 17.5. 17.5. 85.5 and 79. Much less, right? 85.5 minus 79, which is 6.5 degrees Celsius. Yes, definitely there is a huge difference. So, the air gap, the air gap, which is when beaker A was inside beaker B, decreases, decreases, okay, it decreases the rate of cooling, rate of cooling significantly. Yes, and then you need to write down the results. Beaker A, beaker A, you can say no gap, no air gap. The cooling or the difference between the initial and the final temperatures was 85 minus 67.5, which is 17.5 degrees Celsius. And then in beaker B, on beaker A inside beaker B, the difference was 85.5 minus 79, which is 6.5 degrees Celsius. A huge difference. Sun suggests that glass is a thermal insulator, and the experiment does not just test the effect of the air gap. Suggests one change to the apparatus that would test the air gap more effectively. He says that this is an insulator, that this actually affects the readings, right? It affects the Readings. What should I do? Well, you can repeat the experiment with a non-insulator, right? With a good conductor. You can repeat the experiment with a beaker that is made out of metal, right? Made out of a metal, and see whether this change actually affects the rate of cooling or not. Okay, repeat the experiment with a metal beaker B. So instead of beaker B being made of glass, no, you need to change it and make it a metal. Use a metal beaker. Another student repeats this experiment using the same apparatus. State two variables that should be controlled, two controlled variables such as the initial temperature of the water, okay, initial temperature of the water and the volume of the water as well. Calculate the average root cooling rate in beaker A. In beaker A, theta 0 minus theta 180 over 180. Beaker A, 85 minus 67.5. 85 minus 67.5 divided by 180. For the previous question, can I mention the time? Same time taken. Um, you can, but for this experiment, the time is already 180 degrees, and then you are finding the rate of cooling over a specific time. If you want to repeat the experiment with a different time, then the rate of cooling might differ. So this is a whole different experiment. That's why the time, it could be, but again, the final temperature, that's the question. That is the question. If you say that the time is a constant, time should be constant, then the final temperature would differ, right? But if you say that the final temperature is constant and the time would differ, that's why we usually sometimes rather not say, okay, rather not say the time or the final temperature. You have three extremely important controlled variables for any rate of cooling: the volume of the water, the initial temperature, and the room temperature. These are the three critical, okay, these are the three critical controlled variables for any rate of cooling experiment. Okay, the rate of cooling for this experiment would be 0.097. 0.0972 degrees Celsius per second. Okay. Question 3. Sunt investigates the refraction of light by a transparent block. You have a transparent block, then you have a mirror at site CD. Places the transparent block ABCD, draw a normal to point N extending above AB, label the end L. Okay, above AB and label, so it's extending above AB. This point would be L. This is the normal, an L, normal line. Then this one draws line EN. Can I measure the theta, the angle between LN and EN? Can I measure this angle theta? Yes, angle theta using the protractor would be 15 degrees. Soon places pins P1 and P2. Measure the distance between P1 and P2. So the distance between P1 and P2 is very small. Distance between them is 3 centimeters. If your reading is less, it's okay due to the printing error. So it's 3.0 centimeters. If your reading is 2.9 or 2.8, it would be okay. Now, is this distance suitable? Said just whether the two pins are at a suitable distance. Definitely not a suitable distance. Okay? Definitely not a suitable distance. Why? Not suitable. Why? Because you have to increase the distance as large as possible. You need to distance must be at least 5 centimeters. Must be as large as possible, and as we all know, distance must be okay at least 5 centimeters apart. Student places a plane mirror on line CD. Draw a line through points 3 and 4. Extend the line 3 centimeters below CD. Between P3 and P4, extend the line. Okay, so I have P3 and P4. Extend the line 3 centimeters below CD. Okay, so you can measure 3 centimeters below CD. And then label the point where it meets AB, G, lower end H. So the lower end is H, and this point would be G. Okay, repeats the procedure for an angle theta 2, 35 degrees. She places two pins, P5 and P6, so that the pins and the images of P1 and P2 all appear exactly one behind the other. Draw a line through P5 and P6, 3 centimeters below CD. P5 and P6, and extend the line 3 centimeters below CD. Okay, I'm sorry. This should be a straight line. Okay, 3 centimeters below CD. And then point where it meets AB, R, S, and then the point of intersection T. So this is point R, this is point S, and the point of intersection is T, right? Can I measure the angle beta, where beta is the angle between GT and RT? Yes, I can measure the angle beta. This angle, okay. This angle would be around 18 degrees. Should be around 18 degrees. Okay. Hmm. Okay. Student suggests that the angle beta should be equal to theta s, where theta s is calculated using theta 2 minus theta 1. What was theta 2? So theta 2 was 35. Theta 1 was our measurement 15. So 35 minus 15. What's 35 minus 15? This is 20. Is this equal to beta? Well, beta was 18 degrees Celsius, 18 degrees. Are they equal? They are close. Are they within the limits? Yes, I think they are within the limits, right? 20 divided by 18. What's 20? Okay, divided by 18. This is 1.11. 1.11. 11%. 11, okay, percent. Is this acceptable or not? Is 11% acceptable or not? You might say, no, it's not acceptable. Why? Because it's greater than 10%. Someone else might say, no, it is actually acceptable because it's less than 15%. This is a very vague area. Okay. It's a very vague area. The difference between 10% and 15%. Why? Because again, your reading might be beta, might be 19, right? So 20 divided by 19 would be less than 10%. If your reading for beta was 17, your reading would be even, the difference would be even greater than 11%. So this is actually a vague area, 11%. You can say yes and you can say no. You can say both answers would be acceptable. Both answers would be, for my, okay, personally, I might say no. I would say no, not acceptable. Okay, no, they are not equal. Okay, no, not equal. Why? Because 20 and 18 are far apart. Okay, 20 and 18 are far apart, exceeding the limits of experimental accuracy. Okay. The limits of experimental accuracy. If you want to say that the limits of experimental accuracy are up to 10%, it's okay. If you want to say that the limits are up to 15%, again, it might be acceptable. Suggest two precautions. Two precautions in this experiment would be using thin lines and viewing the bases of the pins. Okay. Use thin lines. Make sure your pencils are sharpened and view the bases of the pins. So just one reason why different students all carrying out the same experiment may not obtain identical results. Again, one of the precautions was use thin lines, right? Use thin lines. So what if they used thick lines? Would this give them different results? It would give them different results. What about the pins? If they used thick pins, again, this would give them different results. Whenever you have a mirror, okay, you don't have that many questions with mirrors, but whenever you have a mirror, you can say that the mirror is too thick. Whenever the mirror is too thick, this might give, again, different results. So you can say the pins and the pins and lines are too thick. That's why it's a good precaution to make sure that these lines and pins are thin. Question 4. Student investigates the heating of water using an immersion heater. Okay, an immersion heater is an electrical heater that can be placed into water and you would not be electrocuted. You will not get electrocuted using this immersion heater. Plan an experiment to investigate how one factor affects the rate at which the temperature of water rises. So one factor that would affect the rate of increasing this temperature. The apparatus available includes immersion heater, equipment to connect the circuit, stopwatch, and a beaker containing the water. I guess we have some missing apparatuses, don't we? One factor, one factor that you have chosen. What would one factor that you would have chosen? What is one factor? One easy factor. Again, you have a lot of factors. Yes, you do have a lot of factors. But whenever you choose a factor, whenever you get to choose a factor, always try to choose an easy factor, an easily measurable factor. So an easy measurable factor in this case would be what? An easy measurable factor in this case would be the current, right? The current passing through the immersion heater, right? So if I complete the circuit diagram, I actually need an ammeter, right? You need an ammeter. You need an ammeter. Do I need a voltmeter? Not really. I'm not measuring the resistance. I'm actually measuring the current passing through this immersion. So this is the most important factor. And then, and then, you're actually measuring the rate of heating this water, right? You're measuring the rate of heating this water, which would be using what? Using a thermometer. So you need a thermometer. uh, You need a thermometer inside the water. Okay, this is a thermometer. Okay, inside the water. So you have the water. This is the water level. Okay, you have the water. Then you have an ammeter. Okay, you can say that this is an ammeter. So for my case, for my question, my solution, I would use the current. I would change the current, and based on this change in the current, I would measure the rate at which the temperature of this water is increasing. My range of values, okay, range of values. The range of values would be the current, and I need to, okay, current, and then you need to write down some values for this current. Let's say 1 ampere, 2 amps, 3 amps, 4, and 5 amps. So I have several values for the current. And then range of values. What about the controlled variables? Controlled variables. Volume of the water, volume of the water, the initial temperature of the water, initial temperature of water, the room temperature, and for our case, I might say that the time taken for this whole experiment is constant. Okay, time taken. Why? Because the final temperature would differ, and then based on this change in the final temperature, I can find the rate of increase in uh, rate of increase of temperature of the water. And then the missing apparatuses would be the ammeter, okay, ammeter and thermometer. That's it. Okay, so I stated the factor. I wrote down the key variables. I need to write down the steps for this experiment. What are the steps for this experiment? So first of all, switch on the on heater. So switch on the heater and then leave the heater on for a fixed amount of time. Okay. Measure the final temperature. The final temperature. When you measure the final temperature, find the or calculate the rate of heating. Calculate. Okay. The rate of heating. You don't need to write down the equation. You do not need to write down the equation. Can I write down or can I draw a table? Yes, I can draw the table. What are the columns I need for this table? First of all, the thing you are changing, which is the current. Okay, using using current in amperes, and then the initial temperature in degrees Celsius, time taken in seconds, the final temperature in degrees Celsius. You can add a step, which is change the resistor, change the resistance of the variable resistor, change the resistance of the variable resistor to change the current, to control the current. And then last but not least, you can write down a conclusion. For each value of current, repeat the experiment, and take average, record the results in the table. Okay, record the results in the table. Compare the results. By drawing a graph. Okay, by drawing a graph of the current versus the rate of heating. versus the rate of heating. Okay. Okay.